So this is section 12.7, part 2, and we're ready to calculate some directional derivatives. We're going to be looking at z is equal to the function x squared plus y squared. It's just the surface of sort of a standard paraboloid centered at the origin. Right, looks like this. And we'd like to find the directional derivative at a variety of points and in a variety of directions. First of all, a reminder that we're going to be taking the gradient vector dot product with a unit vector in the direction of motion. So we will need the gradient vector. That's not going to change, so let's go ahead and calculate that so that we can use it over and over. The gradient of f is the vector f sub x, f sub y. So for this function, the derivative with respect to x would just be 2x, and the derivative with respect to y would simply be 2y. All right, so our first directional derivative is going to occur at the point 1, 1, and also in the direction 1, 1. This direction is going to help me get u, but it actually isn't u itself. I'll need to make that into a unit vector, so let's just do that. U would be 1, 1 divided by its magnitude, square root of 1 squared plus 1 squared. So 1 over the square root of 2, 1 over the square root of 2 is my u. That means that my directional derivative is going to be gradient of f dot u. Gradient of f, if I plug in my point 1, 1, this is the x and the y, would give me 2 times 1 and 2 times 1 dot product with 1 over the square root of 2, 1 over the square root of 2, and that's 2 over the square root of 2 plus 2 over the square root of 2, or 4 over the square root of 2. So there's the value of the directional derivative. Let's get a decimal approximation for that. It's about 2.83. All right, just a reminder what that's telling us. That's saying that if I'm at the point x equals 1, y equals 1, about here, and if I walk in the direction 1, 1, so over 1 and out 1 would be on the diagonal, I walk in that direction. What's happening on the surface? Well, on the surface directly above me, I may be started here, and then as I walk outward, notice that this paraboloid would be going uphill. So the slope is about 2.83 along that paraboloid. All right, I won't do them all geometrically, but just to remind us what that's really saying. Let's do a couple more. I want to start at the point 1, 1 again, but this time I want to walk in the exact opposite direction. -1, -1. So my u this time would be -1 over the square root of 2, -1 over the square root of 2. And my directional derivative, gradient of f dot u, would be, again, remember the gradient is 2x comma 2y. This is still the x and the y, so still 2 times 1, 2 times 1. And then it's just my u vector that has opposite signs. So I'm going to get -2 over the square root of 2 plus -2 over the square root of 2, or -4 over the square root of 2. Approximately -2.83. And again, hopefully that makes sense. If I look at the picture one more time, right? If I were to walk in exactly the opposite direction, I'd be walking toward the origin. And notice that instead of going uphill on the surface, I'd be coming downhill on the surface, making it logical that I would get a negative slope. All right, what about starting at the point 0, 0 and moving in the direction of negative 2, 3? Let's see, gradient of f, 2 times 0, 2 times 0, dot u. And I'm actually not even going to bother calculating u this time because that's just the 0, 0 vector. And of course, no matter what u1 and u2 are, I'm going to get 0 plus 0, or 0 here. And keeping in mind 0, 0, that's the vertex of the paraboloid, it would make sense that instantaneously the rate of change there would be 0. All the tangent lines at the vertex are horizontal. All right, what about the point 2, 5 in the direction 3, 4? I am going to need to calculate the u here, so let's just do that. Let's see, that denominator is the square root of 25 or just 5, so 3/5, 4/5 for my unit vector this time. Gradient, 2 times x would be 2 times 2. 2 times y would be 2 times 5. Dotted with that unit vector that we just found is 4 times 3, that would be 12/5. Plus 10 times 4 would be 40/5. Gives me 52/5, or 10.4. Before I go and calculate the other one, let's just talk about that for a moment, thinking about our picture again. I won't maybe draw, but let's just think about it. I'm at the point 2, 5 and walking outward in the 3, 4 direction. Notice that the further away from the origin I get, right, this was 1, 1. If I'm out at 2, 5, out here somewhere, I'm going to be at a much steeper point on the parabola, or paraboloid, and so it makes sense that I would get a larger slope. This was just 2.83, but further out, the steeper slope was 10.4. All right, one more. I'm still at the point 2, 5, so the x and the y haven't changed, but I have a new direction, negative 5, 2, so let's calculate the new u. Looks like my denominator is going to be the square root of 29, so I'm going to have negative 5 over the square root of 29 and a 2 over the square root of 29. So my directional derivative gradient 2 times x would be 2 times 2. 2 times y is 2 times 5, dotted with the unit vector that we just found. And that's going to give me 4 times 5 would be negative 20 over the square root of 29. And here I'm going to get a positive 20 over the square root of 29. And so I get a directional derivative of 0. What's actually happening here is I'm going around one of the contour curves. It must be, this puts me at the exact same height, right? A constant value of z, since the z value is not changing. And I'm actually traveling around one of the contour curves. of my paraboloid. So certainly there are places on this paraboloid where if I walk in exactly the right direction, I end up going right along a contour curve, and I get a 0 change in z. And that's what's happening in that last one. All right, let's take a look at a couple more examples with some different functions. In example 2, we have a new surface, x over x minus y, and I'd like the directional derivative at the point 4, 1, and in the direction negative 1, 2. So I know that I'm going to need the gradient, so let's get that first. We'll need f sub x and f sub y. For f sub x, just a quick quotient rule here. Take the bottom times the derivative of the top with respect to x would be 1. Minus the top times derivative of the bottom would also be 1. Over x minus y squared. And let's see, I'd have x minus x is 0, so I'm just going to end up with a minus y. Over x minus y squared. And since I'm only doing one directional derivative in this problem, I don't have a whole chart, let's go ahead and plug in our point P for 1 right now. Get negative 1 over 4 minus 1 squared, or negative 1/9 for the f sub x. F sub y, quotient rule again, I'll take the denominator times the derivative of x with respect to y would be 0, minus the numerator, and the derivative of the denominator with respect to y would be negative 1 over x minus y squared. And let's see, that's just going to give me a positive x over x minus y squared. And again, 4, 1 is the point that we want to plug in. So I'll get 4 over 4 minus 1 squared, or 4/9. All right, so that means that the gradient factor is negative 1/9, 4/9. Whoops, sorry, gradient of f. What about the unit vector? The direction is negative 1, 2. Make that a unit vector. And that's going to give me negative 1 over the square root of 5, comma 2 over the square root of 5. So if I put this all together, my directional derivative is the gradient vector dot product with the unit vector. And that's going to give me a positive 1 over 9 square root 5, and then a plus 8 over 9 square root of 5. Which is 9 over 9 square root 5, or just 1 over the square root of 5. All right, so hopefully the mechanics of the directional derivative are making sense. Calculate the gradient, calculate the unit vector, and take the dot product. Everything that we've done so far has been based on two-dimensional functions, but it actually works for 3 as well. Once we have our format, right, the gradient and the unit vector, nothing really changes. The only thing we'd have to, of course, keep in mind is that if I have a function of 3 variables, then my gradient is going to have 3 derivatives in it. F sub x, f sub y, and f sub z. So let's give this one a try. This is a function of 3 variables, x squared y z cubed. I would like the directional derivative at the point 3, negative 1, 1, in the direction 4, 2, 3. So I'm going to start with my gradient. And this one's not going to require a whole lot of algebra, so I'm just going to do it on the spot. F sub x would be 2x yz cubed. F sub y would be x squared z cubed. And f sub z would be 3x squared y times z squared. We'll go ahead and plug in our point, 3, negative 1, 1. So I have 2 times 3 times negative 1 times 1 cubed. And then I have 3 squared times, whoops, that's a positive 1 for z cubed. And then 3 times 3 squared times negative 1 times 1 squared. It's going to give me negative 6. 9 times 1 is 9. And 27 times negative 1 would be negative 27. So there's my gradient. Unit vector, our direction is 4, 2, 3. Divide by its magnitude to make it a unit vector. Looks like the denominator is the square root of 29, so nothing to simplify there. And there's my unit vector. And the only thing left to do is to take their dot product. So I'm going to get negative 24 over square root 29 plus 18 over square root 29 plus negative 81 over square root 29. And I obviously have a common denominator. What's that numerator add up to? Looks like negative 87. And I could rationalize that direct denominator. I think that actually would work out kind of nice, but I won't take the time to do it. It's fine like that. All right, so there was some practice on the mechanics of finding these directional derivatives. We'll come back for one last part of this section, and we'll talk a bit more about applications of the directional derivative and of the gradient itself.